Okay, so let's get started. It's a minute or two early, but let me start with some announcements. We have a final exam coming up, so I'm going to give out some materials to help you study for it. So I'll give out the sample exam, which is really last year's exam. Okay, I'll also give the study guide, so you can look at all the material we covered since the midterm and focus on what you need to know. Okay, that will give you some indication of what you need to review for the exam. It's the same deal as the midterm, closed book, closed notes. You can bring one page of cheat sheet, handwritten. You can use either side, so same thing as before. The one thing I will change is I had previously announced that the final exam is comprehensive, which means it covers the entire course. But I will change that to only focus on material since the midterm. Okay, so that will reduce your review stuff in half. You don't have to look at the first half. All right. So, because anyway, the final exam usually focuses on the second half of the course, so might as well just say that explicitly. Okay. All right. There is still a lab out. There is a lablet and a homework out, which is due after the lab. So long as you started the lab on time, didn't take late days. But either way, first focus on the lab first, and then the final homework in the lab. Okay? And then we'll have the exam. All right. So let's get started. So today we will talk about a new topic, which is distributed middleware. There's quite a few case studies. This is a set of case studies. We are not going to go into a super detailed look at any of these systems, but this is just a high-level overview, broad sweep of a set of these systems in the Java world, in the Windows world. We'll look at Blackboard architectures if we have time, but most likely we'll run out of time at the end. And then we'll look at it next time. We'll talk about Hadoop and Spark. So that's what we have planned for today. But before we do that, there are two slides from last time I could not cover, which is still on distributed file system. So last time we talked about XFS and we talked about CODA, which are two file systems that focused on either mobile computing or serverless file systems. But the next two are actually widely used commercial systems. So I'm going to talk about them very briefly, so you at least get a sense of what they look like, how they differ from NFS, XFS, CODA. The first one is HDFS. So this is the Hadoop distributed file system. So this is the file system that is used when you have large data processing applications. Specifically, if you use something like MapReduce that is used for large-scale data processing, the data that is actually used by MapReduce computations is typically stored in HDFS. Okay? So higher level question is, what is HDFS design goal and how is it different from a general purpose file system? So this one and the next one will be special purpose for specific tasks. Okay? So HDFS is designed for high throughput access to application data. So it's really designed for high throughput operations because you are going to read a lot of data, process it, and then occasionally write back some intermediate result. Okay? So it's optimized for large data sets. Okay? So the whole idea here is it's a file system that's optimized for accessing files that might be gigabytes or tens of gigabytes in size. Okay? So how do you design a file system to deal with these kinds of data sets? In a typical file system, the median file size tends to be on the order of a few kilobytes, less than 4 kilobytes often. Okay? So what that means is, on a normal file system, let's say you look at your laptop and you analyze the files on it, you will see that the average file size, even though you might have some small number of large files, the average file size is a few kilobytes in size. So general purpose file systems are designed for smaller files. They do work for big files, but they are optimized for small files. HDFS is the opposite. It's optimized for large files, is optimized for read. Yeah, it also does write, but it's optimized for reads and so on. Yes, but it has a few goals. I'll show you a picture on the next slide. It has to have fault tolerance built in, which means that if some nodes go down, you need the ability to continue to access your large data sets. Okay? Second is it's designed for batch processing rather than any interactive task. So you are not going to use HDFS if you want to open a file in an editor, edit something and write it back. That's not what it is designed for. It's designed for very large amounts of data that maybe is machine learning training data sets, maybe it's some large data processing task. You read it, you process it, you write back some intermediate result. So that's called batch workload. So designed for batch, general purpose file systems are actually designed for interactive, but they support batch as well. Okay, large data sets, and large data set doesn't mean lots of disks. You can also have lots of nodes. Okay, you might have a large number of machines, each of which has a large amount of storage. So this file system spans machines and spans disks across machines. Okay, the other ones we were talking about had, until we got to XFS, XFS, were single machine distributed file system. This one can span hundreds of nodes. Okay, so it, as I said, it essentially assumes what is called a worm model. That's an acronym. Okay, the worm essentially stands for write once, read many. Okay, so what that basically means is the file system is optimized for applications where you create files. Okay, that means you write it out to disk. That's creation. And then you read it many times, but you often don't change a file once it's created. And that's true for data sets. If you think about large image data sets, large text repositories, you don't go and edit that data set. It's a data set meant for data processing. You'll create it and then read it many, many times across tasks. So that's what it's designed for. And then we'll see that it actually tries to move computations to where the data is stored to reduce network and I/O access. Okay, but let me show you a picture of how this works. So there are two important things to keep in mind as far as HDFS is concerned. There are many servers in the system. Okay, servers are used both for computations as well as data storage, right? So if you have a cluster of maybe 100 servers, the disks on the servers can be used to store HDFS data. The CPUs can be used to do computation. So a machine acts both as a compute node and a storage node. Okay, that's the first thing. But as far as the file system layer is concerned, HDFS is concerned, any machine will have one of two responsibility. It will either be a data node or a metadata node. So here the yellow nodes are data nodes. The blue node is metadata node. Okay? And if you remember 2 classes ago, I said what is metadata? Metadata is data about the data. Okay? Every file you store in the system, you have to keep additional information about it, which is called metadata. Typically, owner of the file, size of the file, an index pointing to where the data of the file is stored, and so on. Right? Now, in this case, since our file system can have hundreds of servers, the metadata nodes track for the entire file system, where is the file stored, which machine is it stored, which disk on that machine is it stored, and so on. Okay? And furthermore, since fault tolerance is an important consideration here, okay, the file system uses replication. Okay? So every file, by default, that's a configurable factor, but every file and every block of that file is replicated 3 times. Okay? The degree of replication is 3. Okay? So you create a file, you will basically have 3 copies of every block of that file on different servers of the system. So even if 2 machines go down and 2 of the blocks become unavailable, there's still a third one. Okay? So that's the degree of replication they picked. As you can imagine, if you compare that to the RAID discussion we had last time, okay, we said even mirroring in that case, which just meant that you keep an extra copy for every primary file, was expensive. So here they went with a philosophy that says disks are cheap. We don't need to do parity kind of stuff that we talked about last time. Let's replicate all the files. Okay, so they replicated 3 times. So every file is replicated 3 times, which means the metadata nodes have to track where are the 3 copies of the file. And files are large, so they don't have to necessarily be stored on a single machine. They can be striped or replicated on multiple machines. Okay? So all of this are design decisions they made. Separate the data from metadata. So there are servers that are exclusively just answering questions about you want to access a file, where is that file stored on the machines. Okay, that's your metadata server. And then as far as the data is concerned, you will replicate it twice. Okay, that's a configurable factor, but that's the default. Okay, the replication factor is 3. And furthermore, you will take a file, you will chop it up into smaller chunks. The chunks here will be much larger than typical file system data blocks because the files themselves are large. Right? So if you have gigabyte size files, your chunks or blocks will be megabytes in size, not kilobytes, because that's just too much overhead to maintain. On a normal file system, the block size will be kilobytes. In HDFS, it may be orders of magnitude bigger because the files are themselves bigger. Okay, so many different design decisions, very quick glimpse into HDFS as to how it is different from typical file system. Okay. Any questions about this? This is just a high-level overview. We're not going to get into a lot of details here, but if there are questions, I can answer them before talking about one more. Okay. So the other file system, which we'll talk about, is very similar to HDFS at some level, is the Google file system called GFS. Okay. So it is also designed for large file accesses by and large, right? So it has similar design decisions. As you will see, it uses a notion of a coordinator or a master, which is really our metadata system, right? So you will see it keeps track of data structures and the index for where the file is stored and so on. And then the machines that store the data, they're called chunk servers in the GFS terminology. Those essentially just store the data. Okay? And the chunk servers really run on top of Linux. So this is just a layer. It's not a full-fledged file system. So GFS runs on top of a standard Linux file system. And blocks in GFS are essentially stored as files on the underlying file system. But they will be given name rather than a actual file name. They might be given block XYZ as the name of the file, but that's really a block of a file that's stored at the GFS layer. So you will see at the bottom you have the Linux file system. So again, many servers that are keeping track of where the blocks of the files are stored. That's actually in the master. Okay? But again, you will see very similar design decision. Okay, rather than using things like parity that allows you to store redundant information more efficiently, they just said storage is cheap, disks are cheap, so let's just replicate content, right? So GFS also uses a replication factor of 3, okay? And every file that's stored in GFS is stored on 3 different machines, or at least every block is stored on 3 different machines. Blocks might be distributed across machines. So clients will access a file. So what you will do is you will first do a lookup on the master and look for where the file is stored, and you might have choice of 3 machines to get it from. You can pick one of them and then go access the content from it, right? Because you have 3 replicas to access. Okay. So very similar architecture, okay, as HDFS. And then one last thing I want to mention before we move on are object storage systems, which is what you might have seen if you looked carefully when you did the AWS, the Amazon Lablet. So object storage systems are also a form of storage where you can store lots of information, lots of data, but they are not file systems specifically. Okay? They have a different interface from a file system. In a file system, everything you store will be in terms of a file. The file will have a name. You can open the file and do reads and writes. That's how you access it. Okay? In an object storage system, okay, you can store large amounts of information as objects. So they're called objects rather than files. Objects don't have names, but they have a handle. The handle is like a hash of that object content. So you have to use a handle to get to that object. And then rather than reads and writes, you have what are called gets and puts. Okay, you will use get to get a portion of the object. You will do put to put something into the object. Okay, so similar interface, but not exactly the same thing. It's not designed as a file system. Okay, so it's basically used for large amounts of archival data. And there are many kinds of object systems, but by and large, they make different design decisions from file system. The one thing you will see that's similar as HDFS and GFS is there is a separation of data from metadata. There will be a metadata part of the object storage system that will map a handle that you give, which is an object handle, to the location of that object handle, and then where is it stored and so on. Okay? So this is archival. The canonical example of an object storage system that's widely used is Amazon's S3 service. S3 stands for simple storage service. Okay, that's why it's 3 S's. Okay, and you use HTTP gets and puts to create object, delete objects, and so on. Okay, so you use this for backup, for storing large data sets, and so on. You are not going to use this to do any interactive reads and writes. Okay, that's a very different type of a storage system, largely used in cloud-based system, not in other kinds of systems. Okay. Any questions here before we move on? Yes. So there's a bullet there which says the handles are location transparent and location independent. What that simply says is the handle, think of a handle as a large numeric ID. So looking at the handle, you will not know where the object is stored. The location will not be made visible. Location independent says that internally the system can decide to move the object somewhere else, and then the handle name will still be the same. So it is actually independent of where the data is stored. Okay, and specifically in Amazon's case, okay, it actually keeps its buckets. It also uses a replication factor, but it replicates it across data center, right? So you can have your primary copy of the object, let's say in US East region, which is going to be in Virginia, but it might keep additional copies, one in Europe, somewhere else, in California, and so on. And the reason is they assume that entire data centers can fail rather than a machine can fail. So you keep your objects replicated geographically. So even if an entire site fails because there's a power outage, okay, you will have other locations available. So and the location handle, sorry, not the location, the object handle will not tell you the location, and internally it will figure out what might be the closest available location and get the data from there. So you have all these additional features that are built in to object storage system, specifically in this case S3, Amazon's object storage system. Okay, any other questions? All right, so let's move on to today's topic, which is middleware. Right, so what I'll do is go through several different middleware systems that are out there. These are all distributed middleware system. We'll encounter several of them, so you'll get some sense of how you can use them to write higher level application. Okay, so this is the picture you want to keep in mind. Most of these middleware systems that we'll talk about today are object oriented in nature, right? So, and we have seen this picture before when we talked about RMIs, right? So we have an object, the object is on the server, right? So, and then you can have a client, it has some methods that it exposes, it has state, and then you can access that object from another machine, okay, using RMI methods, exposed methods, right? So that's the picture you want to keep in mind. When the object is distributed, right? So the main thing is you can have this object state itself spread across machines. It's not necessary that the entire object is on one machine, it could be replicated and so on. Okay, that's what we will add to what we have seen before in an RMI one. But this is the picture you want to keep in mind. Okay, so with the first middleware system we'll talk about is essentially Java. Okay, so Java, not the standard Java you write, but the enterprise version of Java. Okay, so Java comes in two flavors: the typical version that we use as developers to write our code, but there's also an enterprise version that is used to write business application. Okay, so this is called enterprise Java. And in the enterprise Java world, there is a additional type of object, okay, that's supported. It's called a bean. Okay, so you can say, how is a bean different from a standard Java class that becomes an object when you run it? So and it's specifically because it's enterprise Java, they are called enterprise Java beans or EJBs. Okay, and we'll see that enterprise Java beans can come in different flavors, but by and large, this is a class that you will write. It will be instantiated as an object. But the new feature that we will add here is the state of that object will persist across invocations of that program. Right now, if you write a Java code and you run that code, any objects that are in your program, okay, or your process rather, will disappear if you shut down the process. If you restart the process, the old state is not going to be there anymore. It's gone. Okay? In this case, because this is a business application, you can persist the state. Right? So essentially, what that will do is it will keep the object state on disk, so that if you restart the code, it will read that object state, and the object state will look exactly the same as it was before. So all of those, it's a stateful class that will persist across restarts of the program. And so that's how you want to keep in mind. Of course, there are other types of beans, as we will see, but one feature that you will not see typically in your standard Java is this notion of classes that or object that persist. Right? So, but other than that, the way you write EJB applications very similar. Right? So there's an interface and there is the implementation of the interface. The interface allows you to create, delete objects. You will have persistent objects, which will be called entity beans. I'll talk about them again in the next slide. Okay, and then we'll see that there are classes that are going to allow you to implement your objects. The implementation of it is the business logic of the application. That's essentially the code of the application that you'll write for each object. Those are the methods and so on. Okay, so that part has not changed. But let's look at now the 4 types of EJB. So first one is what is called stateless session beans. So these are essentially like standard Java classes, except that they don't have any state at all. Right? So if you write some Java class, but there are no private variables, no public variables. Right? So you just have code in them. So you don't really keep state. It does some compute and returns result, but it doesn't have inbuilt state. That's basically the equivalent of a stateless session bean. Okay? A stateful session beans essentially is just more like a standard Java class, right? So it will have some variables that could be state that it maintains, but it's not going to persist, right? So that's just standard notion of what a Java class will do. So it's essentially has notion of a session, it has state, but that state is not going to persist. If you make it an entity bean, it's basically a state that's going to persist on disk. So the EJB code will try to write the state on disk so that if you restart it, any EJB objects will come back as they were before. All the other ones, this one doesn't have state, so restarting it has no impact at all. But this state of the stateful session beans will be gone, right? So those are the 3 types of objects you will have: stateless objects, stateful objects, and stateful object that persist on this. So you have these 3 choices, and then you have something called a message-driven beans that allow you to send messages. And by messages, I don't mean the type of message, RMI messages. You can actually have messages that also persist across invocations and so on. And to explain that, let me go back here. So you will see that in enterprise Java, not only do you have this notion of entity beans, there are additional services that are provided out of the box to write these business applications. The RMI one is there also in standard Java, but you'll see that at least there are 3 more. JDBC is essentially a service that allows these applications to connect to databases. So that's Java database connector. That's what is meant by JDBC. So if you want to access databases, you will use the JDBC service. There is a JMS service here that is basically used for messaging. So you can essentially send messages back and forth, and these messages will be kept and persisted. So you don't need to accept the message immediately. They'll go and sit in a queue, and then you can go and accept it at a later time. So they will be persisted on disk as well. So that's a special type of a messaging service that EJB will support. We'll see it again in the next couple of middleware systems as well. Okay? So this is the world of Java. This is how you can use EJBs and enterprise Java as a middleware system to write higher level applications. Right? So a lot of business applications use EJBs. They can also expose web-based interfaces now. So you can write your web-based applications in this format. Okay, that's one middleware system. Okay, let's look at another one, and then we can try to compare these 2. Okay, the second one is called Corba. Okay, this EJBs are still widely used. This one is actually not used as much. In fact, it was developed and then it really didn't take off at all, and it basically just failed and never became popular. But it's worth at least looking into. And there will be at least one use case I'll explain where it's still in use, but not widely used. But the thing here that you will see, and the reason it's called Corba, is at the heart of this middleware system is something called a broker. Okay? And specifically, it's called an object request broker or an ORB. Okay? And Corba essentially stands for Common Object Request Broker Architecture. It's an acronym which you don't need to remember, but that's what it means. Okay? So what is this ORB? So essentially, think of the ORB as being the communication plane of the middleware. Okay? All the services that this middleware supports use the ORB to essentially send messages back and forth and communicate back and forth and so on. So it's the core of the middleware platform, handles communication between objects and clients, and it will handle all kinds of other things like distribution, heterogeneity, and so on. And we'll talk a little bit about some of what it does. Okay, so the way you will write your application code is, here are your application objects. That's the code you will write as a developer, a Corba developer, but there's all kinds of additional services that will be provided to you by the Corba architecture that you can use to write your application. And I will see there are literally dozens of them, and they provide all kinds of functionality where you can just use that service rather than writing your own code. Okay? So the Corba designers' view was there are lots of things that distributed system developers use over and over again. Okay? Let's abstract them out and make them their own services. And then when you write your application, you use those services to essentially leverage whatever functionality it provides. That was their view. Okay? And they said, so that the services talk to one another, we will essentially use this communication layer, which we'll call an OR. That essentially allows you to do things like RMI. So that's basically sending messages back and forth across machine. Okay? So let's look at, and these services, they're called vertical and horizontal facilities and common facilities, but really don't want to distinguish between them, but let's just see an example of all these kinds of services. So here's a table, it's not even an exhaustive one, that tells you about some service. Okay? So you will see that there's a concurrency service that will allow you to implement thread pools. There's a transaction service that allows you to provide atomic properties on any code you write. There's a notification service that allows you to get notified. Okay, there's a licensing service. If you want to sell your application and give a license, you can use a licensing service for your customers to use, and so on. Right? So there is a persistent service. This is very similar to what I was talking about in enterprise Java, where you can take the object state and you can persist it to disk. Okay? You will see there's a security service that allows you to encrypt information. There's a time service that allows you to do time synchronization. There's a query service. So there's a lots of different services here, right? So what this should tell you, okay, is that this is a very heavyweight middleware, okay, because it has lots of inbuilt services that come out of the box. And even if you want to write a small application, you'll still have to make it work with all of these services, because that is how the designers of Corba intended for it to be used. Okay? So this is actually both a pro and a con. The benefit is lots of this functionality is built in. Okay? The con is that to write even a simple application, there's a big learning curve. You have to go and understand all these services, which ones to use for your application, and so on. And furthermore, it may not be very efficient. If you want to write a small application, you get all of this extra overhead gets built into your application, right? So from an efficiency perspective, it's not the best middleware because it's very heavyweight. If you are writing some heavy-duty application, maybe you will use a lot of those services, and it may be worth that cost to learn all of the functionality and write your code that way. But otherwise, it might not be the best way to write an application. You might be better off just using something simpler like Java, RMI, or some other lighter weight middleware. Okay? But that's how they designed it, and that was also the reason it actually failed, because developers thought it was too complicated. They couldn't write their code in such a complicated system, so they did not adopt it, and it basically ended up not going anywhere. But a lot of the pieces that were built in to Corba have lived on in other forms. So it's actually good to see what Corba did beyond just looking at this table, and see some of these other interesting things that added that we have not seen elsewhere. Okay, so we'll look at 2 or 3 of these things. Okay, first, we'll talk about the object model. Okay, so if you look at this picture, this should look very familiar. It's more like an RMI model where essentially the stub is now replaced by the orb, right? So whatever you have called stubs in RPC and RMI world has become an orb, and you'll see that there's application on the client side, there's an application on the server side. You essentially use the orb to communicate back and forth, right? So that's good, and that's no different. But the thing that Corba allowed you to do that went beyond standard RPC and RMI methods is this notion of dynamic invocation interface, which means that when you write the code, you don't need to specify what object and what methods you are going to call. You can bind to this object at runtime, import its interface at runtime, and then make method calls. So you don't even need to know when you write the code what is the exact object that you might be interacting with. You can essentially dynamically pick an object to interact with, import its interface, and it will tell you all the methods it has, and then you can make those method calls. So that's not something we have seen elsewhere, whether it is in the Java world or elsewhere. you have to actually expose the server methods to the client, and you have to actually name the methods in your code. So if there is a method foo, that's what you will call. Here you can use function pointers and things like that to decide on the fly at runtime what to call. So that's an additional functionality they provided, which other systems don't have. Right? But newer systems, like newest versions of Python, actually support this type of functionality where you can figure out at runtime what methods to invoke. Okay? So that's one thing. The other thing is the RMI calls that Corba supported, okay, went beyond synchronous. So if you remember way back when we were talking about RPCs or RMIs, I said they come in many flavors. You can have synchronous, you can have asynchronous, you can have one-way, you can have deferred synchronous. We saw all kinds of timing diagrams. Okay? All of them came from the Corba world. Right? So when you make an RMI call, you can specify, is this a synchronous method? Is it an asynchronous method? Do I want one-way RPC? Do I want deferred asynchronous RPC or RMI? It supports all of them. Right? So you can decide which one is best for your application. And we've seen all of this before, so I'm not going to go back and explain what they were. But essentially, synchronous was blocking, asynchronous was not blocking. One-way was just you send a request, don't wait for the acknowledgement. And deferred synchronous was to reverse RPC. Right? So this is where it originated from. And some other systems use some subset of this, but Corba supported all of them. Right? So you could figure out which ones to use for your code. Okay? The other interesting thing that Corba introduced was the new, this notion of an event service. Okay? So the way an event service is implemented in Corba is through this middle thing called an event channel. Okay? And this is where essentially this notion of a publish-subscribe model comes in. A publish-subscribe model, also is called a pub-sub model, is a different way of designing a distributed application. We have not actually written any code in this class to write a pub-sub application, but it is still a very popular way for writing certain types of applications. So here is how it works. Okay? In a publish-subscribe paradigm, the components of your applications can either be a publisher or a subscriber. Publisher produce data or events. Okay? Subscribers consume data or events. This is also called a producer-consumer paradigm. Okay? If you have taken an undergrad OS class, you might remember producers and consumers. So that's equivalent here to publishers and subscribers. So publishers will produce data, and they will actually send it to the event channel. Okay? And subscribers have to subscribe to certain types of data. Okay? And they have to actually provide their subscriptions to the event channel so that when a new notification, not a notification, a new event or a data item is published to the event channel, it will check, is there any client that has subscribed to this type of data or event? And if there is a match, it's going to deliver it to the consumer. Right? So the way you want to think about this is you don't actually directly send messages from one component to the other. You use the event channel as an intermediary for communication. Okay? When you produce a data or an event, it's not addressed to any one component specifically. Right? So when you send a message using sockets and so on, you have to specify the recipient, either using an IP address and so on, or when you make an RPC call, the recipient is the other end that's implemented that RPC call. So you know who you're sending your messages to. That's not the case in an publish-subscribe world. The publish-subscribe world, the publishers produce data, they go and sit in an event channel. We think of this as a big buffer, okay? And there are subscriptions. And if there's a match, you will essentially deliver it. Okay? So that's how you will write your application, okay, using a publish-subscribe. Now, this publish-subscribe paradigm can be also implemented internally using a push or a pull-based approach. This figure here on this slide shows you a push-push approach where publishers, which are labeled as suppliers here, are whenever they publish data, they're pushing that data into the event channel. The event channel checks for subscriptions, and for every match is going to push the matched data or event to a consumer. Okay? So both are push. Okay? But you don't have to do it this way. You can also implement an event channel using a pull-pull approach, where you will see that the event channel is periodically polling publishers, saying, is there any new data or event to publish? Okay? And it will pull it and put it in the event channel, and it'll just queue it there. It's the job of the consumers here also to poll the event channel, saying, is there any data to be retrieved? And then if there's a match, you'll retrieve it. So that's a pull-pull model. same event channel, but you're using pull-based techniques as opposed to push, and you can use any combination. You can use push on one side and pull on the other side if you so wish, right? So all of that is supported in Corba as well. Okay, so this is something that's new. We have not encountered this before, and we'll see another instance of essentially using this type of event and notification service. Is this clear? So it's a good way to implement notifications, right? So if you think about your phone apps, they often send you push notifications, right? So the one way to actually do this is to have an event channel where the server side is pushing notification. Your phone has actually subscribed to notification, or the app on your phone has subscribed to notifications. So this is why the system will then push a notification to you. So these kinds of services are implemented using event channels and so on. Okay? Not Corba based, other types of systems, but nevertheless, that's one use case. Yes. Yes, if you want. So that's a good point. If you want to do cache invalidation, the caches could subscribe to events and specify what data they have, and the server could push events when the data is changed. That would be another. Any type of notification, you can use this, and sending invalidate is the type of a notification. Any other questions here? Okay, so there's one more thing here where rather than using a push or a pull, the clients can essentially have an asynchronous notification where you register whatever you're subscribed to with the OR, and then there's a callback whenever there is an event to be pulled, and then you go and pull. So rather than periodically polling, which may be wasteful because there may be no data to retrieve, and the consumer keeps asking, you can use a callback system where you register a callback, and whenever there is some data to be pulled, you get a notification that there is some information. At that point, you send a request to the server and get a response. Server in this case is the event channel, not the actual consumer or the producer. Okay? So asynchronous method invocation can be used to essentially pull data from the event channel. Okay? So that's the thing to keep in mind. Okay? So let's move on to another system, which is called DCOM. Okay, so now we are moving. So we started with Java, EJBs, then we talked about Corba, which was really platform independent. It worked on many different platforms. Now we are going to move to the Windows world and look at some middleware systems that were present in the Windows world. And we'll start from an older system and then get to .NET in just a second. So DCOM is a middleware system that Microsoft designed. It stands for Distributed Component Object Model. Pretty standard distributed object model, something we've already seen. It looks very similar to EJBs in many different respects. Okay? But let me give you a little bit of history as to how this all arose. Right? So the precursor to DCOM was something called COM. Okay? COM essentially stood for Component Object Model. So think of COM as a way you can do RPCs, but really on a more of single machine. Right? So if you have a system of processes that want to communicate with one another using an RPC-like interface on a single machine, in the Windows world, you use COM. Right? And the reason Microsoft came up with this COM layer was they had all kinds of windows. And so there were scenarios where these processes needed to communicate with one another. So this was their RPC-like layer. Okay? But it's designed or optimized largely for single machine communication. Okay? And then on top of COM, okay, so they added another layer called OLE, which was object linking and embedding. Okay? So the OLE layer was designed specifically for Microsoft Office applications to talk to one another. Okay? So you could, for example, take a figure that you made in PowerPoint, and you could directly embed that into a Word document. Okay? That's called object embedding. Right? So you're embedding one object into another. So now, or you could create a bar graph in Excel, and then you could put that bar graph in a Word document. Right? So you could directly drag and drop it, and then somehow Word knows how to talk to Excel and import all of that. And if you updated the Excel document, the Word figure would automatically change because Word and Excel are talking to one another. And they are essentially using RPC messages back and forth and using the OLE layer to communicate. So that allowed you to embed one object into another. Specifically, you can now view Excel spreadsheets, PowerPoint documents, Word documents as object, and each object can then import or export other objects from it. So that's how they essentially layered OLE on top of that. And then when you had essentially web-based document, they added another layer called ActiveX that allowed you to do something similar in the web world, but we'll ignore that for just a moment. But then eventually you needed an ability for machines to communicate with one another, and that got you into DCOM, where they made the whole thing distributed. Okay? Eventually, DCOM was renamed .NET, which is still what they use today. Okay? .NET just added language independence. So in this case, you could essentially write the client in one language and the server in another language, and to still allow communication, similar to how gRPCs were language independent. You can have RPCs that go across application components that are written in different languages. Okay? As just a brief history, every 10 years, I think there's a new name and a new layer that gets added, but we are still in the .NET world, okay, which is the Microsoft middleware that you use to write applications using Windows. Okay? But at the heart of it, still an object-based model. Okay? Still has very similar. So this was the history that I just already mentioned, which I'm going to ignore in this slide because I already talked about it. But let's now look at how DCOM and .NET works. So if you look at this picture, it looks very similar to everything we have been talking about. Your client machine, the object is sitting on the server machine. You'll see that there's a stub at both ends. Okay, there is something called a registry, which allows you to register what objects are where and so on. That's called the service control manager. Okay. But the way communication works, very similar to RPCs and RMS. So you can have communication go back and forth. And there are some similarities to the Corba world, which we will ignore here because that's not really important. What is important is this is still by and large a distributed object model. And furthermore, it has very similar features to what Corba has. So you will see that there are persistent objects, which are called essentially monikers, which allow you to take an object that was created on a previous instant and load it back from disk. Right? So you can create persistent objects just as you had entity beans. You have something called a moniker, which is like a pointer to an object that allows you to reconstruct an object. And there are other repositories where you can store the object state, retrieve the object state, and so on. So it has standard objects like Java does, but it also has persistent objects because they wanted to have similar functionality to what is there in EJB and Corba to write business applications. Okay? So similar, very similar things. The persistent object is one thing that they added to standard RPC model. Is that a question that you? Okay. All right. So it was a very quick overview through several different systems. Okay. But by and large, nothing very other than the event channel. Really haven't learned anything new because we have already looked at RPCs and RMIs and used it. Only new other thing was that you can persist the state of your object. Okay? But now we'll talk about a very different kind of system, which is called a distributed coordination model. Okay? Now this is going to go back to lecture 2 when I talked about blackboard architectures. Okay? And I'll restate what I had said then because you probably forgotten what I had said maybe 20 classes ago. So, but distributed coordination systems are basically used to implement blackboard-based architecture application. So let's try to understand what this is and how it works. Right? So first I'm going to present a taxonomy. Okay? It's a little bit abstract, but then we'll try to make it more concrete and I'll explain what a blackboard architecture is. So this is a taxonomy of how clients and servers might interact in any distributed application. Okay? And you'll see that there's a table at the bottom here, which tries to classify all of these distributed systems in 4 different buckets, depending on how they coordinate in the temporal dimension and how they coordinate in what's called the referential or the physical or spatial dimension. Okay? So in either dimension, your coupling can be strong or weak, which is written as coupled or uncoupled, and I'll explain what coupling means and so on. Okay? But let's take the simplest thing, which is you are coupled in both dimensions, where you will say I'm coupled in referential and temporal, which is labeled as direct in that box. Okay? This is essentially all the applications you have been writing, where the client and server are both executing, okay, and they are both communicating directly with one another. So this is essentially say they are coupled in both time and space. Coupling in time means the client and the server have to be running at the same time. Then you are coupled in time. Okay, coupled referentially means that they actually need to know who they are talking to. Right? The server has to address the client, client has to address the server. You need to know their IP addresses and so on and so forth. Okay? So this quadrant is all the applications you have encountered so far. Okay? Now let's look at the other three, which you probably have not encountered. And so we'll make the couplings weaker in one or both dimensions. Okay? So let's essentially take the one that is uncoupled in the temporal dimension, but coupled in the spatial dimension. So a good way to understand this is an email application. Okay? Email is a way to communicate, just as client server RPCs is a way to communicate. Okay? But when a sender sends an email to a recipient, there is no expectation on the sender's behalf that the recipient is actually logged in and actively checking their email. Okay? The email will be delivered and read at some later time. Right? So now you are decoupled in time. Okay? You are communicating with someone where they don't actually have to look at that message immediately. They can look at it at some later time. Right? So that is essentially called a mailbox-based communication, where you are decoupled in time. But it is coupled referentially because every email is addressed to someone. So you know who you are sending the message to. Right? So essentially, if you know the recipient and you mention the recipient in your message, that means you are coupled in the referential dimension. And a temporal means that the sender and the recipient are both communicating actively at the same time. Right? So if you relax this, you have essentially a mailbox-based architectures where you are decoupled in the temporal dimension but coupled in the referential, the mailbox coordination. Okay? So if you go on the other dimension where you are coupled in time but decoupled referentially, you essentially have a publish-subscribe paradigm that we just talked about. Okay? Because remember, in the publish-subscribe paradigm, I said when you publish an event, it's not addressed to any particular recipient in particular. You just say, here's an event, you put it in the event channel, and consumers decide which events they want to take from the event channel. So unlike RPCs, which are sent to a particular server, okay, unlike email, which is addressed to a particular recipient, the publish-subscribe world, messages are not addressed to any particular component in the system in particular. You just say, here's an event, you publish it. Right? So that gives us this meeting, also called meeting-oriented, because in a meeting, it's like you call a meeting, but you announce that there's a meeting, but it's not addressed to a particular person or a recipient. It's the same thing. Okay? So this is called meeting-oriented. Okay? And then the last one, okay, which is what we are going to talk about today, is called generative communication. We are decoupled in space and time. Okay? So here, clients and servers or rather components of the system are communicating through some messages, but the messages are not addressed to anyone in particular, and neither are the senders and recipients communicating at the same time. So it's decoupled in space and time. Okay? That's called generative communication, also called blackboard-based architecture. So there's an easy way to understand how you can be decoupled in space and run the referential and temporal dimension and yet communicate. Right? The best way to understand this is the same example I had actually shared in the earlier class, which is, let's say there is a notice board, right, where you can go post notices. Right? So you know what that means. Right? So you can go and put a notice there. Say, let's say you are moving, you want to sell your furniture. So you make a flyer saying that I have to sell my sofa and all of this furniture, and you post a note, and then you put your contact information there. Right? So now you created a message. Okay? You put it on this notice board. It's not addressed to any particular person. Okay? You just put it as general interest and you put it there. Okay? So you don't know when you publish it who is going to see it, whether anyone will actually want it or anything like that. But you just posted a notice. Right? Now maybe somebody comes at some later time. Maybe they want to see if someone is selling furniture, and they scan notices. They look at your note and they say, okay, maybe I'll contact this person and see if they still have furniture to sell. Right? So the communication has now been decoupled in time because you posted the note and somebody might have come days later and looked at your note. Right? So it's not the communication not happening at the same time. The sender and receiver are not communicating in real time here. So there is some time lag between when the data was published and when it was consumed. Okay? And as in this example, any data you produce is not addressed to any particular recipient. You just put it on the notice board and somebody else comes and takes it later. Right? So this type of communication, this is why it's called a blackboard or a notice board architecture. You post notices on this shared system, which looks like a blackboard. Someone then comes and takes it at some later time. Is that example clear? Okay, so it's clear why it's decoupled in referential and temporal dimensions. Yes, your question. Okay. Question is, in publish subscribe, why is it coupled in the temporal dimension? Yes, so the point is that the event channel does not buffer messages for long periods of time. When an event is published, it checks what subscriptions are active and immediately delivers it. So if a client comes 2 hours later, you are not going to go, you missed 100 messages and deliver it. So that thing does not exist, right? If you did that, you are essentially back in this blackboard architecture. So think of a blackboard architecture as something like an event channel which persists messages. So you can come back later at any point and look at past messages. In event channels, it's all real time. The sender and the receiver have to be running and you get delivery immediately. Is that clear? Any other questions here? Okay. So we will look at a case study of this system called Genie. It's a system that was developed in the Java world that essentially implements this bulletin board model. Okay. So let's think about, I was giving this example of a notice board, right? But you should ask, that's not a distributed application. That's a real world example. Which real distributed application might use an architecture of this sort? Why would you want to write an application where you're communicating with entities you don't know? Okay, you just publish some messages and someone else comes at some later time, looks for this. So what examples can we think of where something like this is useful? Any thoughts here? Yes. Yeah, you could do social media. Yes, that's what. Although you will not use a blackboard-based architecture there, you could post messages and someone else can come take a look at it. That's very close to what I was talking is a bulletin board, physical bulletin. But any other lower level systems application, not like a user communication oriented application. So one example you want to keep in mind is these types of architectures are used for configuring your system on the fly. So there's entire class of systems that are called zero conf services, zero configuration services, and I'll give you an example so you'll understand what I mean, where you don't have to pre-configure something on a system. You can come and discover services and configure them on the fly. So here's an example, right? So let's say you take your laptop and you go and visit a friend. Okay, you connect to their home Wi-Fi network. Okay, and now let's say you want to print a document and they have a printer in their house. Okay, what is the normal process you would have to go to print a document? Anyone printed anything? Yes. You would search for the printer. So you have to configure the printer because you went to someone's house, you never printed there. That printer won't be pre-configured in your machine. Right? So you'll have to configure the printer, you'll have to add information, configure it, potentially get the driver, and it'll print after that. Right? So what if you could simplify this? Right? So in this case, your machine can go and discover what printers are available. And when you say, I want to print, it will just say, here is a list of nearby printers. And it will show you that printer. Okay? You will just say, I want to print to that printer, and then it will configure itself and print it. Okay? That makes your life as a user much easier because you don't have to go and manually do anything at all. Your system went and figured out this is a new Wi-Fi network. Here's a printer that seems to be available. It showed you that printer. You just said print. Your life is good. And this is, by the way, how your modern operating systems work. If you go into some environment, it will show you a printer. If you have an iPhone and you actually look for a printer, it will show you nearby printer because it's able to discover it. But what does this have to do with the Blackboard architecture? So this is how you can implement this Blackboard architecture. Services can advertise themselves using a Blackboard. Okay? In our example, the printer would go and post a notice on this Blackboard architecture saying, I'm a printer, I'm HP model XYZ, this is my IP address, port number, and so on. Okay? And your machine just has to go and look for, is there a printer service being advertised on my Blackboard architecture? And it might find some number of printers and show. And there might be other services. Maybe there is a storage service, or maybe you are essentially having a streaming service that's for your house. It can show you all kinds of services that have advertised themselves. Right? So this can be very easily implemented using a Blackboard architecture where services are advertising themselves. Other machines come look for services. In this case, you're looking for a print service, and then you find them, and then you configure the machine accordingly. Okay? So the printer did not know beforehand when it advertised itself which clients will come and print. So you couldn't send a message to a laptop saying, I'm a printer. If you ever need to print, here is my IP address. You couldn't do that because you don't know who is actually going to ask for this print service. So you are better off advertising somewhere where some other machines can come and go discover this service. So for things like service discovery, okay, which is something you actually implement in distributed systems where you can go and discover services that are available in your network, you can use Blackboard architecture because you can advertise those services and go and discover them on the fly. Right? So nothing needs to be pre-configured or told to you. Right? So that's an example of where you would use a Blackboard architecture. Okay? Now, with that background, let's look at how would you implement this type of middleware. Okay? So in the Java world, you will implement this using what's called a Java space. Think of a Java space as essentially a replicated database. Right? Every record in the database is a notice or a service that's being advertised. It's a tuple. A tuple basically, so you publish a tuple, it advertises something. It's like you go and post a note in your system. So, and then you have essentially publisher subscriber type scenarios where you publish data items, they will persist. So this is not like an event channel in this middleware. They are going to persist in this system. So they'll just stay there as if the note has been posted. Someone else can go and query saying, show me all matching printers or show me all notices that match a certain criteria. So you send a query, or you can even make a subscription and be notified. You can do either of these, and then you will be given whatever is matching in that bulletin board architecture. Okay? So this system that you see at the bottom, that's essentially a database. That's where you're in the Genie world is called a Java space. So you're publishing data items that go and sit as tuples in there, and then when you query them, you will be getting tuples that match. Or you can have a subscription which says, if there's ever a matching item that's published, notify me. Right? If a new printer appears, notify me, and then you will be notified. So you can do these two things here. Right? But there are some, and this is the example I was just talking about. Right? So here's your Java space where you can write, and then that will publish some item. You have written A and B, and then this third client here essentially goes and looks for some data item, and it can retrieve it. When you retrieve it, you have one of two choices. You can remove it from the Java space, because if you say this is a one-time item that I consume, nobody else can consume it, you'll have to remove it. But if it's a long-standing tuple, then you just leave it there because someone else can come and ask for the same data item. So you can have both of those functionality in your Java space. Okay? And the way you are going to implement this Java space, as I said, okay, so I'm going to show you, is it's a replicated database. So you will see here that, that there are two figures here. At the top figure, you will see there's the database is replicated 3 times. So also on the bottom figure. And the way you are going to decide how to replicate is one of two kinds. Either you are going to say that all writes are broadcast, which means every tuple is going to be put in all of those replicas. Okay? So this is the equivalent of, let's say you have a notice board on each floor of this building. Every notice is going to be posted on all of these floors. Okay? That means if I'm looking for something, I just need to go to my local notice board and look for it, because every node is replicated. I don't have to go to another floor to look for something, right? So the same is true here. If writes are broadcast, reads are going to be local. That means if I'm going to query something, I just go to one of the replicas query. I don't need to look at anywhere else. Okay. The opposite is also true, where the write can go to a local one, where that's the equivalent of I go and post a notice to the nearest notice board. But now if you're looking for something, you have to query all of them. Right? So in this case, reads are going to be broadcast to all, writes are local. So either you have local writes, broadcast reads, or broadcast write, local reads. So this is how Genie allows you to configure its Java spaces. Right? So this one is essentially showing tuples are broadcast, reads are local, but the opposite can also be true, which is essentially shown in the second figure, where write is done locally, but the reads actually have to go to all of them. Right? So this is how you will implement your Genie-based architecture. Right? So internally, it's a database that's going to store all of your information, and then it will support queries on top and the ability to write to the Java space. Any questions here? Okay, so that was, yes, your question. Okay, question is, in the example of a home Wi-Fi network, where will this exist? So, so if you actually use Genie, which a home Wi-Fi network does not use, but let's assume you use this system, you would be running a Genie service on maybe some computer on your network, and it is going to be advertising itself. Okay, so that's how you would implement Genie, but that's not how your home Wi-Fi network works, because there's no real bulletin board that's implemented. So the other way you will essentially implement service discovery, okay, is that every service is broadcasting its identity continuously on the network. So every second, a printer is going to send a broadcast message, say, I'm a printer, I'm at this IP address. It doesn't go into a bulletin board. It's like I go and keep shouting every so often saying I'm a printer, and then if I'm looking for a printer, I just wait for the next broadcast and I find it. So there are two ways to do service discovery. The Genie world is where you are going to post your information into a shared tuple space and you go retrieve it for that. The other one is you essentially send broadcast messages that goes to every machine in the network, and then the machine just has to listen. And when it sees a broadcast, it will basically add it to its list. That is how some of the things that Apple does actually. So they are essentially listening for broadcast because they don't use this type of service, which is more efficient. But broadcast means you'll keep sending this information over and over again. Okay? But that's certainly a way to implement it. Yes, your question. Okay, question is in the Blackboard architecture, and I'm going to go back to this figure. The clients can communicate at each time the server should be running. So when I said that components were decoupled in referential dimension, temporal dimension, I was talking about client. The server has to be running, but the server is not directly communicating, it's just facilitating the communication. So it is these components that are decoupled in space and time, not the Java space itself. And so Java space has to run. It's not like you publish and the server disappears and comes back. That's not what we're talking about. These are the components that are decoupled. Okay. All right. So very quick overview of two more systems, and then we are done. So I'm going to quickly talk about distributed data processing middleware systems, specifically Hadoop and Spark, which if you've taken this class systems for data science, you probably looked at this in a lot more detail. But just in case you have not, I'm going to just show you what these applications. So these are middleware systems that are designed for data processing. They're for compute and data processing. They support all kinds of scientific applications, which are also called big data applications. There are some examples here: genome sequencing, looking at lots of images and processing it. These are brain scans. You can think about lots of financial data being processed, a lot of clinical data. So in many different scientific domains, there's lots of data, big data sets, and you've got to process them. And these middleware systems are designed where you can use a cluster of servers. Okay? So that's why it's a distributed system where you are parallelizing the processing across multiple machines. Okay? So it's parallel processing of large data sets. So that is what these middleware systems are going to give us. So large data sets We need to parallelize the process. So here's an example of how you could do this. Okay? So this is called the map-reduce programming model. So the way you have to implement a map-reduce based programming model is you have to take whatever application you have that's doing the data processing, and you have to essentially map it to two stages. There's going to be something called a map stage, which is going to be the first stage of the processing. And then there's going to be the second stage, which is called the reduce stage. And so here is how it will work. So you will essentially have a lot of machines. Okay, here there are 3 of these nodes that are shown, but typically you might have dozens. Okay. Each of them is going to read some chunk of data. Okay. It will do some pre-processing on that data, and it will decide which of the machines to send it on the second stage. Okay. So you read some information, you do some processing, and then you do what is called a shuffle. The shuffle says, where do I send it next for phase 2? Right? And so you will see this, all this black arrow says some data that's processed by node 1 goes back to the reduce on this node and on node 1, and this one goes to node 2, node 3, and so on. And then once you get it in the reduce phase, you do the final processing. Right? So essentially, you are going to have 2 stages of processing, okay? The map stage and the reduce stage. And then there is going to be a data exchange, which is the middle stage, which is called the shuffle. Okay? So you have to write your application in this format, okay, for you to figure out how to do some large-scale data processing. So just as an example, let's say you want to do a simple application. You are given a lot of text files, and you want to do word count. Word count simply says, I want to count which words are present in this text file and how many times they occur. That's what a word count application is. Right? So let's try to ask a simple, in this map reduce case, how are we going to essentially A, parallelize this processing, and B, construct a map reduce version of the word count program. Right? So it should be clear how you're going to do this sequentially. Right? If you just had one machine, you're going to sequentially read all of your text files. You're going to construct an index, and for each word, you will have an entry. And if you encounter the word, you will increment that entry. So at the end, you know how many times each of the words have occurred. That's a sequential way of doing word count. How will you do this in parallel? Okay, so in particular, let's try to map it to this 3-stage process. Any thoughts on how to do this? Is a canonical example of map reduce. Not very hard to figure out if you've done things like merge sort. And the first thing is we have a lot of text data. So we'll partition it. Right? You'll say node 1 does the first third. There are 3 nodes, right? So node 2 is going to look at the second third, and the node 3 looks at the last third of the data. So you took your data, partitioned into 3. So I parallelized. Okay. So now what do I do next? Okay. Node 1 can start reading its information. Right? So it will start encountering words. Right? And we got to count these words. So how do we do this? Okay. So you can create some index structures and decide how to count and shuffle. So how are we going to do this? I'll give you very simple. There are many different ways to do this, but here's a simple one. Okay. Let's take the words, okay, because the words are going to start with from A through Z. We'll say all words from, let's say, A to D are going to be counted by node 1. All words starting from A to D, and then E through some other letter will be node through, and then this will be node 3. So you partition the word space into 3 chunks. Okay? That's what we did. So now node 1 reads some text, and it finds the word apple. Okay, it's going to say, I'm going to send that to the node 1 of the reduce phase, because it's responsible for counting all words starting in A. Okay? Or if you get, let's say, pair, then you will say, I'm going to send that to node 3, because that's the node that's counting all letters, all words starting with P, and so on. So that's your shuffle. So you read words and you decide which of the nodes to send it to for counting. The reduce phases are actually doing the counting. So the reduced nodes are going to keep receiving words from the mappers, and as they get each word, they are going to keep that index that we talked about. So here you'll keep index for all words starting from A through C. Every time a word comes in, you increment it. And the same thing here and here. So at the end of this, you read all the words, you send it to the reducers. The reducers count. You now have an index that has actually counted all the words in parallel. Is that clear? That's a very trivial map reduce program where you just parallelized your data processing. Right? So given any type of computation, you have to write it in a map reduce format where you have to see what is the pre-processing. In our case, there was no pre-processing at all. You just have to figure out what is the starting character of the word and then decide who to send it to. That's all we did. All the counting happened here, but there could be other applications where you actually do some processing here and some processing here, and there's some data exchange in the shuffle. Yes?
What is the use of multiple?
Okay, question is, what is the need for multiple mapping process if each process reads entire data? So each node does not read the entire data. If this is a large corpus of text files, let's say you have a million text files, each of it has some text, you want to count words across all of them, you will say first 33% of the files are responsibility of this node, next 33% here. So each of them is reading different information and then parallelizing it and counting. That's why it's not doing it. If you read all of it, then you don't need more than one mapper. You can do it with one. Is this clear? Okay. All right. So that's MapReduce. There is a platform that was built to do all of this, which has lots of different subcomponent. The one that we did talk about already is HDFS, right? So in Hadoop, Hadoop is a system that implements MapReduce. The data or the text files in this example I was talking to you would be stored on HDFS. You will have lots of these files, and these nodes will be reading from HDFS, doing the shuffle, and then eventually the mappers will write out the final results back to HDFS. Okay? That's the only component we have actually encountered, but there are many others. We'll talk about Spark in just a moment. There's an Edge-based, that's a database. There's Kafka, that's a messaging service. There are Yarn and Mesos, which implement scheduling and so on, which we will not talk about. Okay? Mesos we did encounter, if you remember, resource offers, right? So that is the scheduling framework that Hadoop actually came up with, and then it works with Hadoop Mesos as well. Okay? So this is the ecosystem which we will ignore, but what I will do is talk a little bit about one of those, which is called Spark, which has become a very popular data processing platform. Okay? So here is essentially Spark. It's an Apache project. Okay? It was built on top of MapReduce. Okay? And I'll explain what it does. So it's more efficient than doing MapReduce, and we'll see why. Okay? But what it supports on top of it is all kinds of higher level. You can make SQL queries, you can do machine learning training, you can write graph-based applications, and so on. For the purpose of this class, ignore all of that. Okay? Just assume you have the MapReduce model, and we'll see how Spark makes it more efficient. Okay? So what happens in the MapReduce model, okay, is when you do the shuffles phase, okay, the shuffle data can be written out to disk, and then the reducers have to read it back from disk. Okay? So the mappers read the original data from disk, they process it, and they create new intermediate files that are stored. So you might create a file for node 1 to read. That's your intermediate output. So shuffle could be direct messages you send, or they could be data you write to files, and then the reducers read those files and process information. Okay? Because the amount of data is large, you can't always store it in memory necessarily. So the shuffle phase sometimes involves disk I/O. Okay? This significantly slows down the data processing, because any I/O, as you know, is slow. Disks are slow. Compute is fast. Okay? So you are going to essentially slow down your MapReduce computation because there is intermediate I/O in between. Okay? Spark has tried to resolve this problem by saying that let's not store the data in disk. We will essentially create a distributed memory cache. Okay? So in the shuffle phase, instead of writing the data to disk, we will write it to our in-memory cache. Okay? And furthermore, the reducers in this case can go and read it from an in-memory cache rather than actually reading it from disk. But this is a distributed in-memory cache, because any single RAM of one process or one machine is not going to be large enough to store large data set. So you will take all the RAM that's available on all the machines, create one big logical cache, okay, which is basically going to be a union of the physical caches on each of the machines. Okay? So essentially, this system implements the equivalent of what is called distributed memory, which we have not encountered at all in this class. This is the first time I've actually talked about something called distributed memory. So just think of distributed memory as no different from physical memory, where I can go and access any location on memory, but now I can access memory locations on other machines. Okay? So that's the concept of distributed memory. Okay? The way it's implemented really is it's a distributed cache, because you basically have the cache is stored in memory. So I'm actually accessing cached items that are stored on other machines, not just my local cache. Okay? So it is going to implement this concept of distributed memory. Okay? So objects are cached in RAM across the cluster, and essentially every intermediate output is constructed, or not constructed, is realized as something called an RDD, which is an acronym for resilient distributed data set. Okay? So what Spark does is, whenever you produce any intermediate output, you create this object called an RDD that's essentially stored in memory. Okay? But as you can imagine, okay, machines can fail. Okay? Memory is volatile. So the machine reboots, the data is gone, machines can fail, and so on. So if I'm going to rely on this cache for my subsequent stages of the computation, because remember, this is just intermediate output. I generated an output, I stored it in RAM. Okay? The next stage is reading it, one machine rebooted. Somehow that data is gone. Right? So I need a way to reconstruct that data. Otherwise, I will not be able to complete the next stages. So RDDs automatically allow you to reconstruct the data by tracking which computation produced it. And if a machine fails and I have to reconstruct the RDD, it will re-trigger the computation that the RDD was created from and reconstruct it. So here we are not keeping redundant copies. Right? One way to deal with failures is I create redundant copies. One machine fails, I go to another one. Right? But RAM is not going to be a resource that you have in abundance. There will be less memory than your disk. So you cannot actually use redundancy. So we will do recompute as a way to construct it. So you will have your distributed cache. The distributed cache will store objects called RDDs. Every RDD object will keep track of which program and what code generated it, what data set generated it. And if the machine fails, the Spark system automatically regenerates it for you. So it will just look like access has become a bit slow because that data is being regenerated. Right? But so long as machines don't fail, okay, this is going to run much faster than MapReduce, because all the intermediate output is stored in RAM. Okay? So you're reading from memory rather than reading from disk. So you can do all your MapReduce style distributed processing, but much, much faster. That's the main advantage of Spark. Okay? This is why it's become very, very popular. You talk to anybody in database world or anybody who do large-scale data processing, they will actually use Spark to do their work. So, and it has basically more or less taken over what MapReduce used to do 10 years ago. Now everything is done in Spark because it used in-memory caches as a way to speed up your computation and keep them in a resilient fashion. Is that clear? Okay. Any questions? I'm not going to go into a lot of the details here because that's not important. The main concept is distributed memory, which is implemented as a distributed cache. Because RAM is volatile, we have the ability to reconstruct any cached objects that disappear because machines fail. Those are the two concepts that are the most important that allow you to build on what MapReduce does. Okay? So with that, let's end it here today, and we'll continue next time.